guess. What else? Ah, that's it. Okay. So yeah, in the previous semester, in the energy chapter, we have said that some forces are conservative, meaning that the work done by these forces can be expressed as the difference of some quantity. So it's something that's can be computed easily. And then to compute the work done, we just define the concept that we called as the potential energy. So it appears that the electric force is one of such forces. So as a result, we need to define some electric potential energy. And then we will see that this, well, instead of potential energy, it's better to use the potential concept. And so as a result, we will be working with the potential actually, and instead of the potential energy. In any case, by using the potential and seeing its relationship with the electric field, we are going to say a few things. I mean, we will sometimes compute the electric fields from the potential only. And I mean, we are going to see problems like computing the potential due to an continuous charge distribution and things like that. At some point, I'm going to talk about the potential energy of a charge distribution towards the end. But I mean, most of the time, we will be talking about the potential. Right, let's just start with this. I'm just going to claim it without proving. But from the Coulomb's law, this should be apparent. In the case of gravitational force, I think I have somehow shown that the gravitational force is conservative, and then we have deduced this gravitational potential energy from it. Since the Coulomb's law is essentially is in the same form as the gravitational force, it should be kind of obvious that why this is conservative, right? So as a result, I'm not going to show this. I'm just going to claim it, right? So let's remember this. So let's say it like this: F is conservative. Okay. There's some kind of a force, right? Gravitational, electric, or whatever. So there's this concept of work done by the force. So work done when I move an object from an initial position to a final position, right? This can be expressed as the integral of the force dotted with the displacement. Right? This is the basic definition, but there's this kind of integral in here. And then we have said that, well, this can be expressed as the difference of something. So I can just write this thing down as the difference of something, and then we put a minus sign in front so that this becomes the negative of the change in the potential energy. And let's remember the change in here. So it's the final minus the initial. So if this is the electric force, let's say, so that's the force work done by the electric force. So that's the electric force. And this is the electric potential energy, right? So as a result, once I express the energy exchange due to the electric force in terms of its potential energy in the work energy relationship, I don't use the work expression anymore, right? That's something that we should keep in mind, and that's why we have a minus sign in here, right? Let's do it like that. So yeah, I think I reminded you this. So as a result, if you don't understand anything from what I'm saying in here, please go back and refresh your knowledge. So that's one of the critical points that you should understand. Otherwise, you might meet some problems later. It's a conceptual problem, so sometimes this will produce a difficulty in here. So therefore, the work done is somehow related to the potential energy. And from the force, we just compute the work done like that. Or I can do the same thing for the force. I can compute the force from the potential energy. So if the integral of the force is the negative of the potential energy, so therefore the derivative of the potential energy, let me write it down like that, with respect to the coordinates, and gives us the corresponding forces. Let me say etc. in here. I'm not going to say anything more. Okay. So here, I'm just going to do this, right? So first, I need to go to this. I need to basically pass the potential concept. So I'm just going to do it like this. So I'm just going to consider the motion of a single point particle with charge Q in the presence of other particles, in the presence of other charges. Why I'm considering this? Because I can work done by the electric force. I can consider this quantity for a system of particles, in which case I need to add up the works done by the electric force on all charges. Forget about all, just concentrate on one. That's what we are doing. I mean, we just start with the simplest one. So we have a little charge in here. There are many other charges in here. So there might be some positive and negative charges, whatever. So as a result, there's some kind of an electric field produced in this region in here, whatever. So this charge somehow, I don't know, moves from that location to that location. So this just moves under the presence of this electric field produced by other charges here. So I know that force applied on this charge is equal to its charge multiplied with the electric field. When the charge is zero, I know that there's no force, and so therefore there's no work done. So therefore, I mean, force is proportional to the charge, obviously. What else? So therefore, the work done by that force is equal to the integral of this expression. And so therefore, yeah, whatever. So basically, this is equal to Q times something, an integral of the electric field. Right. I'm just going to call this as the change in the negative of the change in the electric potential energy. Now, what happens is that, I mean, if the charge is zero, no force, and therefore no work done, no potential energy, right? So somehow you can see that the potential energy must be proportional to the charge, right? Just like the force is proportional to the charge. So there's this proportionality in here. Potential energy is also directly proportional to the charge. And it is basically the charge of the particle multiplied with some quantity that doesn't depend on what kind of particle that is. So this thing basically, the remaining thing depends only on the other charges. So that's the reasoning behind why we define the potential concept, okay? So let's say it like this. So, right, F is proportional to charge. So therefore, potential energy, electric potential energy is also proportional to charge. Let me write it down like this. Electric potential energy. So therefore, we define, I mean, we can write down the electric potential energy as charge multiplied with some quantity. And so therefore, the change in the potential energy is basically charge multiplied with the change in the potential. So let's say it like this. So in that case, we are going to call V as the electric potential. All right, so this is going to be due to all of the other charges excepting this one. So I'm going to state it in at some point in here. Just a moment, let me think about this. I have to be careful in here. Um, so we define it like this. So therefore, from here, therefore, work done can be expressed as, well, it's the negative of the change in the potential energy. So therefore, it is the negative of the change in the charge times the change in the potential. And I know that this is equal to Q times the integral of the electric field. So therefore, we basically have some kind of a parallel expression in here. So instead of an integral of the force, I'm taking the line integral of the electric field between 2 points, and this gives me the change in the potential. All right. Basically, this is the work potential energy relationship, but we now write it in terms of the electric field and not force. We write it in terms of the electric field and the potential. Okay, so let's talk about the units then. All right, how should I talk about units? So I think I'm going to do it like this. Yeah, I'm just going to do it in that corner. So that's units. Units of potential. Okay. Since the potential is potential energy divided by charge, the units of potential is basically it's joule divided by coulomb. It's the joules per coulomb. And joules is kilogram meters per second squared, kilogram meters squared per second squared, right? So in terms of the fundamental units, it's like that, all right? But since this is something, it's a unit that's frequently used, people gave a special name to it. We just call it as volt and write it with capital V. So that's basically from Alessandro Volta. He is the one who discovered the pile, the battery, if you remember. So to honor him, we gave this unit his name. So we use this unit. So since this is a commonly used unit, like in everyday life, for example, we would like to express other units in terms of these. So one of them is the electric field in here. So you can see that the electric field multiplied with length is equal to the this potential expression. And so therefore the units of the electric field should also be like that. So as a result, we sometimes use for the unit of electric field. All right, let's just remember that this is newtons per coulomb from our previous definition. In any case, we can also express it as volts per meter, right? Because if I take, whatever. I mean, from this equation in here, you can see that the electric field should also have the volts per meter unit. So you can easily check that these units actually satisfy this relationship in here, because Newton meters is joules, and so the volts is joules per coulomb. You can easily see this. So as a result, for the electric field, we sometimes use either of these expressions. Okay. So what else? I think that's it about the units. So I don't need to say anything further in here. Okay. All right. So I think this has to be given at the very end, but I'm going to, first let me do this. I'm sorry about that. So let's explain again, right? So I think we had this charge distribution in here. I'm just going to do it in the same way that I have done before. So I have some charge distributions in here. everything except this plus Q charge, whatever. So they produce some kind of an electric field in here. What we do is we define an electric field at every point. Okay. So let's say it like this. We define, and sorry about this. Did I say electric field? No, the electric field is already defined. So we define a potential energy. A potential V of R for every point R in space. So basically, this potential is due to all charges that produce the given electric field. Or the mentioned electric field or whatever. So if I'm talking about the motion of the charge little q, for example, in that case, when I compute the electric force on this one, I just compute the electric field produced by all of the other charges except this little one in here, right? So as a result, I mean, because a particle cannot apply a force on itself. So as a result, when I'm computing the force on this charge little q, I forget about the electric field produced by this one. So this one is kind of important. So as a result, this is something that we have to forget, okay? And when I'm therefore computing the potential for the motion of that particle, I need to consider only the other charges that apply a force on this particle. So as a result, I need to consider only the electric fields produced by these charges, all right? So there's some kind of a subtle point, but that's somewhat important in some cases, actually. So as a result, you have to take into account the fact that a charge cannot apply a force on itself. So as a result, a charge cannot experience a potential that it produces, right? Some microphone is apparently open. Okay. So in any case, we define a potential in here, and then when we actually what we do is like we just consider the potential at two different points, perhaps in the motion of the particle between these 2 points. So in that case, the change in the potential, basically the final minus initial, that's equal to the potential at the final point minus the potential at the initial point. Just a moment. I think I'm going to open the users. Okay. All right, so this then apparently is equal to minus there's a minus sign now, so the integral from I to f of the electric field dotted with dr. All right, so therefore, this is basically, this potential, we say that is due to the charges that produce that electric field or something like that, okay? So let's quickly pass to the other thing. So let's say it like this. If I and F are very close to each other, so that means this delta R, let's say RF minus RI, this is very small. Yeah, forget about it like that. So that is very small. In which case, I can write this integral expression like that. It is minus, yeah, that's approximately true. But it becomes exact when you take the limit where this delta R really goes to 0. And so again, let's remember that this is a dot product. So therefore, this is Ex times delta X plus EY times delta Y plus EZ times delta Z. So as a result, if you set, for example, delta Y and delta Z to be equal to 0, in that case, you can, you get this term, and so therefore you can get EX. So from here, we just deduce that the electric field, X component of the electric field is the derivative of the potential with respect to X. And I can do the calculation this time for Y. I just set delta X and delta Z to be equal to 0. And so on, right? I mean, we just do this, did this calculation before. So we have the same kind of a thing in here too. Right, so as a result, if I know the potential, I can get the electric field. If I know the electric field, I can also get the potential. Right? So we have then these two relationships that relate the potential to the electric field. So one is the integral of the other, and the other is the integral derivative of the other one. And there's always a minus sign in front. All right. Again, the same discussion as in the previous semester about the potential energy. The value of the potential energy at a point is not well defined, because in physics, we always meet the changes in potential energy. All right? Only changes in energy basically enters into the discussions in physics. Let me say it like this. Physically observable quantities depend only on the changes in the energy, and therefore changes in the potential energy. And I can do the same thing for the potential. So let's say it like this. I'm going to write it as a comment in here. So all physically, let me say measurable quantities depend only on changes in potential. So let me say delta V. They never depend on only on potential at a given point. Okay, so as a result, the potential at a given point is basically unphysical. We say it like this. So, but the potential difference between 2 points, this is physical. Okay, this is another way of saying this, right? So this is usually expressed. So what's the potential at that point? People usually, I mean, there's no well-defined answer to that question. What is the potential difference between these 2 points? This is well-defined. I can measure it. Everybody can measure it, and whoever measures it, they are going to find the same result. But what is the value of the potential to that point? We need to attach a value usually, but different people can attach different values. So some people will say that, well, I'll take the potential at that point to be equal to 0, so it's 0 for me. Some people will say that it is minus 100 volts and things like that. And so as a result, everybody can disagree about the value of the potential at a point. So that's why it is, I say that it is unphysical, right? It never enters into the physical expressions directly. It always appears in the difference. So, I mean, once you define a potential at a point, the value of the potential at other points has a well-defined value. And so therefore, these kind of expressions are always the same. Okay. Another way of saying this is this, right? We can define a new potential function, let's say V nu, by adding a constant to V, let's say, and it will be a valid potential. All right. So I define the value of the new potential at a point R as the potential R that somebody has defined plus C. I add like 10 volts, right? For example, C is equal to 10 volts, let's say. So if somebody says the potential in here is 0, I say that it is 10 volts. So in that case, this is unphysical, but the physical quantity, which is the change in the potential, is always the same. So therefore, we will agree with what the change in the potential is, and we will compute the same change in kinetic energy of the particles and things like that. So that's okay. But the value of the potential is is something that can be shifted, right? I mentioned this before, but I mean, I didn't explain a lot. So that's what people call as the gauge transformation, or it's a special case of a gauge transformation, right? I talked about this gauges before, gauge symmetry and things like that. This has nothing to do with the gauge symmetry. Well, it has something to do with gauge symmetry. So to express the symmetry, we use this gauge transformation. But it's not just that, right? There's some other thing in there too. So you will be learning about this gauge transformation later in electromagnetism class, I believe. But this is the basic, actually. So somehow it tells you that if you just shift all the potential values by a constant amount, the physics doesn't change, right? That's the symmetry, basically. But it is a slightly different symmetry than all the previous 3 basic symmetries that we have seen. In any case, it appears to be a very important symmetry, right? There's another way of saying this thing in here. We say that we can define the value of potential at a given reference point to be anything we want. And let's say it like this. Well, and the potential at all other points are defined accordingly. So I don't know. So I mean, just choose a reference point, and then, sorry, what is it? Some kind of a reference point choose, and then define the potential in here to be equal to 0. In that case, define the potential at R as basically the negative of the integral of the potential. All right, let me just say it like this, all right? I'm going to talk about this in a moment, but usually what we do is like we just choose the potential at some special point to be equal to 0. And then to compute the potential at any other point, we just evaluate an integral from that point to some other point. And so as a result, we just define it like that. But we have to choose, and this is a choice, we have to choose a reference point. For point particles, usually this reference point is at infinity. I'm just going to mention this. But this is one quantity that we can use. One information that, yeah, this is one of the things that we actually use a lot. So there's always a choice involved in here. So to be anything we want, so there's a choice in here. This is just like the gauge choice in here. Okay, let me then continue with this. So potential due to a single point charge. Right, we have a single point charge Q. Yeah, let's say it like this. This is an electric field produced. These are the electric field lines. Um, and we would like to find the potential at a point which is at a distance r from the charge. What's the potential at that point, right? That's the question that we would like to find. We would like to solve now. We know how to solve it, all right? Actually, I need to evaluate an integral of the electric field. So that's the only thing that we can do, basically. But let's remember this. What's the origin of that problem? Origin problem is this, right? We have started with this. I have a point charge, capital Q in here, and a point charge, little q. And I'm moving that little q point charge from some initial location to that final location. And I would like to compute the work done on this charge with, this particle with charge little q, right? I don't know how to express this. So I need to compute this. So to compute that, it's the work done by the electric field. To compute that, I need this potential difference, right? So this is the original problem. There are actually two charges involved, but now I forget about this charge in here. Forget about it, because I only need the electric field produced by the other charge, this one in here. So as a result, that's why we are looking at that problem in here. So I have just a single point charge. I'm going to compute the potential produced by, due to that point charge. And then once I solve that, I will be able to consider the problem of moving some other charge against this one in the presence of this one, and then compute the work done on that other charge. Okay, I mean, that's the original problem. Let's just keep this thing in mind. But in any case, we will be, this is going to be our basic expression. Once we deduce this, then I can compute the potential due to any kind of a charge distribution, because I would be basically adding up the contributions of all of the point charges. All right, let's do it like this. So I'm just going to consider this motion. All right. This is my point charge. So I'm going to move from one initial point to the final point. And I need to compute the change in the potential. That's basically VF minus VI. And I know that this can be expressed as the integral of the electric field from I to F. And then the question is, which path should I choose? Should I choose a wiggly path like that? Or should I choose a more regular, I don't know, more direct path like this? Or some other path? Right, so it appears that there's actually a nice path in here. So let me first of all draw these lines. Right. All right, these are lines, so let me stress on these 2 points. So the first point has an initial distance of Ri to the charge. The second point has a distance of Rf to the charge. So there's nothing in here, right? It's just a point in space. And I would like to compute the potential difference between these 2 points. So I can move like that. So first I can move in a circular path like that, keeping my distance to the charge the same, and then moving in the radially outward direction. Or I can move radially outward and move to that point, and then move in a circular path. These two are the simplest, and we need to use, we can use these two, but I mean, since we know that the electric force is conservative, this is given, this is something that we accept. So in that case, I mean, I don't need to try all of the possible paths in here. So I just choose one path and then do the integral in here, and I know that at the end I'm going to get the same value. So as a result, forget about this. And so as a result, consider this path. Okay. So I'm going to do it like this. So I think I'm going to move this a little bit and then change the magnification a little bit. So as a result, I'm going to write this integral as an integral over the first path plus an integral over the second path. Second path. Yeah, well, there are these additional minus signs always appearing on the right-hand side. Why not? Okay. So over the first path, so in all of these paths, I'm going to do it like this. I need to have some kind of I need to compute the electric field there, and then a displacement. And I need to compute this dot product in here. And similarly for the other one. Yeah, I think I'm going to do the magnification in here. So as a result, I need to just do this calculation in here. So let me magnify this point in here, right? I'm going to start with this part of the curve. So I know that. I mean, what I need to do in here is this. So let me raise this. I think I'm going to choose something like that. Yeah, this is the first path, part of the path. But in any case, right. So there is an electric field in here. I know that the electric field is radially outward. So it has some kind of a radial component multiplied with the radial unit vector. There's a displacement in here. So the displacement, I'm going to show it with this color. So it's always parallel to the path taken. And because of that, these two vectors are perpendicular to each other. So let me call this as dr. This is a small displacement. And so therefore, it's always tangent to the path that I'm taking. And so because of that, let me use a white color in here. So the dot product of the electric field with the displacement in here is basically the magnitude of the electric field multiplied with the magnitude of the displacement, multiplied with the cosine of the angle between them. And since this angle is equal to 0, E dot R dr is equal to 0 in here. So that means on this part of the path, the work, the potential energy, potential doesn't change. The potential doesn't change, right? There's no contribution to the change in the potential coming from here. I mean, from the point of view of energy, if I move a charge, another point charge from this point to that point, along this circular path, in that case, I don't need to do any work done on. There's no work done on it, right? So it's the same reasoning. So for the case of work done too. All right. So that means in here, on this part of the path, this integral is equal to 0. And whatever we get from this integral. So therefore, this is just the integral over the second path only. And this also tells you that the potential difference only depends on the distance between the radii, this Ri and Rf, right? So let me draw this one in here and two in here. So along 2, however, we have a simpler thing. So let me again magnify this. So along the second path, the electric field is in the radial direction. I don't know if the radial component of electric field is positive or not. It might be negative, but let's just draw this picture as if it is positive. What's my displacement? Well, my displacement is along the radial direction too. So therefore, my displacement is basically the change in the radial coordinate multiplied with the radial unit vector. So here we have these two unit vectors which are parallel to each other, sorry. So these two, they are parallel to each other. And I think I'm going to do it like that. So for this case, for this pair, then my calculation would look like this. So it's the dot product of EDR. So it's basically E multiplied with dr multiplied with the R unit vector dotted with itself, but that's equal to 1, so therefore this is EDR. All right, I mean, this is the case where we can easily see what the dot products are, so we basically get rid of them easily. So sorry about that. I'm not perfectly comfortable with this. So in any case, so that's an integral of, yes, that's the integral of the electric field, which is E times R, multiplied with the change in the radial distance, multiplied with the R unit vector. It's a dot product. And this radial coordinate changes from the initial radial distance to the final radial distance. And that's the change in the potential. There's a minus sign coming from the definition of the potential change. So in any case, the rest is just simple calculation. So that's an integral from Ri to Rf. That's EDR calculation. I know that that's equal to 1 over 4 pi epsilon 0 q divided by r squared dr. So therefore, this is minus q over 4 pi epsilon 0, which goes out. It's an integral of basically r to the minus 2 dr, right? But I'm going to write it down like that, so that the integral is r to the minus 1, and there's a minus 1 coming to the front, because if I take the derivative, the coefficient should disappear there. So that's Ri, Rf. And so that means this is like, right, this, at the final point, the value of the function is minus 1 over Rf. And at the initial point, it is minus 1 over Ri. Their difference is this. Together with the minus sign in front, then I'm going to get this. So that's the change in the potential is Q divided by 4 pi epsilon 0, 1 over Rf minus 1 over Ri. Right. I know that this is equal to the potential at Rf minus potential at Ri. And the question is, how can I find the potential at, for example, Rf by just looking at that equation? And the answer is we cannot. It's mathematically impossible. The only thing that you can say in here is that the potential at the final point is equal to Q divided by 4 pi epsilon 0, 1 over Rf, plus some constant, right? For some constant C. And it's the same thing for the initial point. So as a result, if you take the difference of these two expressions, this constant disappears, right? So as a result, with this constant, this equation is correct. So that's therefore, this is the only general solution that you can provide, right? So, I mean, when you compute the potential from this expression alone, there's always a constant involved in here. Right, this is the potential due to a point charge, sorry, it's a point charge at a distance r, therefore. So the potential due to that point charge is apparently 1 over 4 pi epsilon 0 q divided by r plus a constant. There's a constant involved in there. So that's what we have found. However, what we would like to do is to basically get rid of that constant. So for this reason, we have to make a choice. And what we do is we choose the potential at infinity to be equal to 0. So I think I have said the same thing for the gravitational potential energy too. We choose r equals infinity as a reference point. And set the potential there. I mean, potential due to discharge there to be 0. So we just define the potential at infinity to be equal to 0. So that's definition, which means if I insert into that expression, this would imply that that constant is equal to 0. So setting that constant equal to 0 corresponds to choosing the infinity as a reference point. This is something that's important to realize. So we just make a choice in here, right? So we just pick the gauge in a way, pick the potential at infinite to be 0. And because of that, this is basically what we say. So that's the potential, therefore, due to a single point charge. All right. Let me draw the picture, and then it's the same picture over and over again, but let's be clear in here. So potential at that point, therefore, is equal to 1 over 4 pi epsilon 0 Q divided by R. So the potential due to a single point charge at a point is given by this expression. Okay, so let's give a break in here. After the break, I'm going to, we will check how we can compute the electric field from here. And you will see that, yeah, it's, I mean, the potential also contains the electric field information as well. So let's stop the recording.